Hello everyone, we are Team microGPU from EE6350 VLSI Lab, sponsored by Apple and guided by Professor Minggu Sok. I'm Tian Yun.
I'm Yuntian. I'm Yangfan.
I'm Yuxi.
I'm Alice.
I'm Adrian.
I'm Fengze.
Our project is a 3D renderer which takes in 3D information, camera and lighting configuration, and render the corresponding 2D image. Now, let's take a more detailed look at our project.
The project initiated from our strong interest in computer graphics, and the team wanted to bring some visual rendering into the VLSI Design Lab. We initially explored an open source project that could render two surfaces with 4 vertices. It supported 6-bit color output with static lighting, and all the matrices are pre-computed in software. Building on that baseline, we decided to take a significant step forward and define our own project. The new project renders objects with more than 2,000 surfaces and over 1,000 vertices. The chip also supports dynamic lighting effects with 24-bit VGA color, ensuring smooth transition on a surface boundary. Also, we aim to accelerate all the matrix computations in hardware. Overall, running at 250 MHz, the design can render 3D objects at a resolution of 640 by 480, 60 frames per second. This is our newly designed architecture. Let's look at some of the key blocks. This is where the pipeline starts. The input assembler collects all the rendering configurations, including the object orientation, position, camera viewpoint, light direction, and color settings via the UART interface. We implemented a UART receiver with a baud rate of 115.2 kilobits per second, along with a deserializer that packs the byte data into 48-bit packets that the downstream modules can recognize, and stores them into the FIFO. After IA receives all necessary settings for one frame, the vertex shader will start the vertex transformation. It first constructs the matrices using the parameters from IA. One of the matrices is for aligning the object, camera, and light to a unified global 3D coordinate, while the other one performs the actual 2D projection and screen space mapping. Vertex shader retrieves all the model vertices from the memory and applies matrix multiplications to transform them. The BF module consumes the 3D vertices after the viewpoint correction. Along with the index information, it generates the normal vectors for each of the triangles and uses them to determine if a surface is visible from the camera and what its corresponding light intensity should be. The next stage is the triangle rasterization. The rasterizer processes all the visible triangles using their 2D vertices. It will find all the pixels inside the triangle's bounding box and store them in a tile buffer. To speed up the computation process without interfering with the VGA scanning, we have designed a ping-pong buffer mechanism, with every 4 rows as a tile, allowing the rasterizer to compute the next tile while the VGA outputs pixels from the previous one. In addition, it maintains the depth buffer for correctly rendering overlapping pieces. The final stage of the pipeline is the actual RGB color computation. Using information from light intensity memory, color memory, and tile buffer, the PC module can calculate the exact 24-bit color for each pixel. It also synchronizes with the VGA controller and drives the output bus. And now let's move on to the system modules. The scan chain is responsible for issuing the global reset and configuring the clock generator. Also, it initializes the memories, and that's how we load all the 3D model data. In addition, the scan chain can configure the test FSM, which controls the status of the core clock and set the on and off cycles. The design includes a large number of memories accessed by multiple modules, with some of them dual port and mask-on. To manage this, a dedicated controller is implemented to arbitrate between accesses from scan chain and all the key modules. Now let's talk a bit about our design flow. The project began with designing the reference model, which is a standalone C++ application that implements the algorithms and renders the objects. This model helped us to understand the required computational complexity that we needed to support in hardware and also served as the golden reference during verifications. Next up, the team spent extensive time working on the RTL design. We focused heavily on parallelizing the data flow to ensure the throughput. As we used a fixed point across the stages, we carefully tuned the format to balance the area and precision. We've also integrated a few designware library modules such as division, square root for better timing. Also, since the ultimate goal is to drive a VGA monitor with 60 frames per second, the synchronization logic is another critical aspect of our design. For each individual blocks, we prepared dedicated test benches with random stimuli. Lastly, we have designed our own test FSM and integrated all other system modules. After preparing all the individual blocks, we conducted end-to-end verification at the top level. The core of this process was a test bench composed of two parts. One is the C++ driver that handles the model file processing, UART command generation, and output image collection. It also forwards the hardware-generated output to a comparison script that validates the image against the golden model. We also reused this driver in our final demo. The second part is the system Verilog test bench, which manages the timing of the scan chain and UART sequences. The two parts are connected through system Verilog DPI with exported functions. This end-to-end test bench has been deployed in all our verification flow, from RTL to post-synthesis and post-APR.
After the initial version of the RTO code was finished, we started working on the synthesis and generated the netlist. And after that, we started to work on the most time-consuming part of the project, the automated place and route. In our first attempt, we tried to do it hierarchically, which is how people usually do the APR, by doing the submodules first and then the top. However, this method wastes too much area since all the modules have to be in the shape of a rectangle. Thus, the first design decision we made is to decide to do the APR directly on the DUT level, which is shown as the green GPU core part here, so that it can fully utilize the space on the chip. We ran the entire design flow several times, modifying RTO code as mentioned previously, and made other improvements in the APR stage. First, it is the placement of the SRAMs. Now we place them according to the data path and then adjust it a little bit to allow the best routing strategy for the tool. It is actually a really critical step because at first we just placed it randomly on the chip and what we got was 2 days running the APR with thousands of DRC errors. The second improvement is the shape of the SRAMs, which is decided by the number of mixes in the SRAMs. We tune a few times to get the best shape for every SRAMs in order to have an optimized space for the other logical routing. And of course, we also did some parameter tuning for further optimization. After about 1 month finishing the placement for the DUT and other system modules, we started working on the IO path. There are some strategies we did and we would like to share. The first is actually decided in the previous APR stage that we sacrifice one side of the IO paths for more area. We can see that we only have 3 sides of IO paths here. Apart from the input and output signal paths we needed, the power paths required are the dirty VDD, DVDD, and the clean VDD, CVDD here for path power supply, the VDD for chip core power supply, the VSS path for ground, and the POC paths for path enablement. At first, we just equally distributed the remaining paths to these 4 kinds of power paths. But then we started to worry that if it's enough, since we have the 24-bit VGA color outputs and other synchronization signals. Thus, we increased the number of path-related power paths CVDD and DVDD to make sure that we have enough driving strings for our output. For placement, we just equally distributed the power paths everywhere to ensure enough current for every path. And we inserted the ground path between the signal output sets to improve signal integrity.
And this is the result after the place and route process and after the seal ring and dummy filling. Here shows our package. Due to the huge number of paths we have, we chose the larger package, CCQ100. After we got our fabricated chip, we designed the essential circuits on the PCB to test and use our chip. The 5-level shifters are for converting the signal voltage between the FPGA 3.3 volts and the chip pad 2.5 volts. The 2 pairs of input and output GPIO are for receiving the chip configuration data from the FPGA and for sending out the VGA color and synchronization data to the FPGA. LDO is a must for providing a stable source voltage, which are the 3.3 volts FPGA VDD, the 2.5 volts DVDD, 1 volt CVDD, and 1 volt core VDD. The power source is coming from the battery or power supply. And of course, we added other probing IOs for debugging. Regarding to the PCB here, we want to share more about our design mindset. When talking about the power stability, we made 2 improvements. The first is to add the coupling capacitance to avoid a sudden voltage drop. And the other is to add the power and ground plane to provide a low impedance power and return path for the current. So we have a 4-layer PCB here. When arranging the components on the PCB, we placed them according to the data path to minimize the wire length, and to distribute the decoupling capacitance and the ground vias to ensure overall stability. On the left is our final PCB with components. Our testing and demo plan is shown in the diagram. The software is running on the Linux kernel to load the 3D model, listen to the keyboard or camera, and send out the configuration data to the transmitter. And here we use the FPGA hardware as the UART and scan chain transmitter to our chip. And we also use the VGA DAC module to receive the output from the chip and to drive the monitor. Now let's show you our demo.
This is our demo setup. This is the FPGA we're using, and this is the PCB, and those are connected through this 40-pin GPIO, and the board is powered by the external batteries. Here's a close-up of the PCB board. The chip in the middle is the 3D renderer that we designed. Now let's look at some of the basic functionalities of our chip. First of all, rotations around different axes. And light direction changing. And translations. Real-time color changing is also supported. So this is the blue one. If we turn on all the 3 RGB channels, we can get the white apple. And now we're having a more colorful model. As you can see, each individual triangles has been assigned with a unique color. At this point, I'm turning off the lighting effect, so you can see that there are no more shades and all the surfaces have the same light intensity. Other than rotations, You can also make much more complex animations with translations. So here is a bouncing ball. Furthermore, other than just keyboard, we have another interactive way to control our chip, integrating a hand recognition system. Another PC is running the hand detection program, and it will forward the commands to FPGA through Ethernet and eventually controls our chip at real time. And this is a better angle to look at how the movement and orientation of the hand actually control the object at real time.
We want to send our appreciation to all the people who help us. And first, I want to thanks to Professor Minggu Sok.
Thanks to Professor Stephen Edwards and his embedded system class.
We also wanted to thank you for all of the students in this class for supporting each other.
Special thanks to Apple for supporting and sponsoring our project.
Also, many thanks to our TAs, Dawang, Shantang, Mosen for their support and guidance.
Thank Richard for all your assistance in the lab.
And thanks all the other people who helped us along the way, and wish you all the best.